Welcome to Technical Founders. My name is Carlos Lara, AI Technical Founder, and today we will learn how to perform machine translation with TensorFlow and Keras. This is an artificial intelligence system that is able to convert text from one language into another language. So in this particular case, in this example, we will convert English text into French. So our input, our features, are English sentences and the words in those sentences, and the output, the labels, are the French translation of those English sentences, those sentences and the words. So the first step here that we need to do is actually do some imports. So we're going to import collections and import NumPy and import our libraries from TensorFlow and Keras. So we have Tokenizer to tokenize our text, and this is part of the preprocessing. Pad sequences function also from Keras preprocessing sequence, and then we're going to do some import from model, some layers, optimizers, losses, and so on. So in this particular case, we're using TensorFlow 2 again, and first also we want to verify access to the GPU because we're training on sequences of data. So these are recurrent neural networks, and training actually is just not feasible unless you're using GPUs. So here we're making sure that we have access to our GPU. And now the data set that we'll be using is actually this data set right here. So we have English text, English sentences that already have some pre-processing in them. And then we have the French translation for those sentences, just here in text files. And as you can see, the punctuations have been delimited using spaces, for example, commas and periods. And all the text has been converted to lowercase. So this is going to save us some time with pre-processing. So we want to go from English, which are the features, all these words and these sentences, into the French translation. So that is machine translation in artificial intelligence. So we're going to call our load data function, our helper here, a module, and we're just going to pass in our vocabulary files here that we just saw. So that we store those in these two variables, English sentences and French sentences. And then the next step is let's actually take a look at our data, what we have here in code. So we can actually just look at our sample. So for sample I in the range of 2, so we're just going to look at two examples, and then English and French sentences, and that's what we have. The complexity of the problem is determined by the complexity of the vocabulary. So a more complex vocabulary is a more complex problem. There's going to be more parameters to learn, it's going to take longer, and so on. So let's look at the complexity of the data set that we're working with here. So we're actually going to create a couple of variables here, counters, for English and French words. These are just dictionaries that map unique words to the counts, the number of times those words appear in the text. So we're going to do here some list comprehensions. So for sentence in English sentences, and then another one for word in sentence dot split. So we're splitting the sentences into words, and we're just grabbing those words and counting them and creating a dictionary again of the counts for unique words and a corresponding ID for them. So we do that for both English and French, and we do some prints here just to see what we have. So for English here, we have over 1 million English words. Same with French, and then for English, 227 unique words in this particular data set, and then 355 unique French words. So they don't match, obviously. They're different languages, and we want a deep neural network, a deep learning model that is able to generalize and correctly will go from English to French, regardless of the length and the different vocabulary sizes and so on. And here we can print also the most common words in each one of those data sets. And it's pretty reasonable here. What we see is what we would expect. Now the next step is actually to do some pre-processing. So there's already some pre-processing in our text as we saw, but we want to do some more pre-processing, right? Our neural network is like a huge mathematical function that is composed of tensor operations, matrix multiplications, that kind of thing. So it doesn't accept just text. We need to convert it into a mathematical representation. So the first step that we always do is to tokenize. So we're going to tokenize the words into IDs. Now this is a word level language model, not a character level. because we're translating the words in those sentences. And we also want to add padding. So we want to tokenize the words into IDs and then add padding to make sure that all of the sequences are of the same length. So here we have a tokenize function here that we wrote, and all it does is really, so we create a tokenizer object, and tokenizer is from Keras that we imported earlier. And for this parameter character level, we're going to set it to false because we're not doing it at the character level, we're doing it at the word level. So we have our object, and now we're going to call the fitOnText method on that object and pass in our input data, our list of sequences to be tokenized. And this is really going to create a specialized tokenizer object for this particular input, and you'll see in a moment why we want that. And so we're going to return a tokenizer object dot text to sequences, passing in our input. So this is going to grab our strings and tokenize them and convert them into integers, into a mathematical integer representation. And we also want to return the tokenizer because we'll use it later, because the tokenizer also contains a dictionary, a mapping from words to IDs. So let's look at an example here. So we have a text sentences here, just as a sample list of sentences, and let's call our tokenize function that we just created here on our text sentences and return those two return values, the actual tokenized text and the tokenizer itself, and let's print it out. So as you can see here, what we get printed here so it's what we said, we want the text tokenizer, our tokenizer specialized for this input because it contains the word index, so the mapping from words to indices. So each unique word here, as you see, corresponds to a unique integer ID. So that's how we'll be able to go back and forth. So we have that, and then we're going to also print out some basic stats. So let's actually go ahead and enumerate and zip our text sequences and our text tokenized. So we're going to print first, so sequence 1, 2, and 3. So we enumerate them, print the samples, and then the actual input, what went in. So first the first sentence, and the second, and the third, and then the actual output that we get. So that's now is our having converted from text into integer IDs. However, you can see here these are different lengths. These sequences are not the same length, and that brings us to the next point, which is we want to add padding to make sure that they're the same length. And padding really means adding zeros at the end of the sequence up to some length to make sure that all of them are the same length. So let's actually create a function here called pad, and it's going to take in our input that we're going to pad, and then an optional length parameter. So if the length parameter is not specified, we're going to look at the sentences in our input. So X, a list of sentences. So for sentence in X, in this list of sentences, we're going to grab the length of the sentence and put it in a list. And then we're going to grab the maximum value in this. So basically this grabs the length of the longest sentence in this list of sentences, and that we assign that to our length variable here. And then we're going to return the value from this from pad. So pad sequences we imported from Keras Preprocessing to pad our sequences, a very nice built-in function in Keras. So pad sequences, we pass in what we want to pad here, our list of sentences X, and then for our max length parameter we assign it the length that we got, whether it's specified in the function or whether we got it here by looking at our lengths. And then padding we set post because we wanted those zeros, those paddings to be added at the end of the sequence. So let's go ahead and look at a test pad here. Let's test pad variable, assign it to the pad function that we just created, and pass in our text tokenized. Text tokenized is what we have here, our text sentences, but tokenized that we're using just for testing here. And as you can see here, this is the input, what we had initially. But as you can see now, the output gets padded according to the maximum length. So the maximum length here happens to be 10. As we see, we actually printed that out. So it's 10. So anything that is shorter than 10 is going to have zeros added to that sequence until the total is 10. And here you can verify. See, this was a shorter sequence as we saw before, and it received actually 5 zeros. 1, 2, 3, 4, 5. And this one was already 10, so this one stays the same. So now that we have tokenized the words into these integers, and then we padded, now we're actually ready to move forward. So that's very standard in natural language processing. You would want to do that as part of your pre-processing pipeline. So now we're going to grab our data. So we're going to write a pre-process function here that takes in the features and the labels. So our English text and our French text that we saw here. Apologies, not this one. Would be this here. So as you can see, we have that, and now we want to tokenize each one of them. So X would be the English and Y would be the French. We're going to tokenize both of them and return the pre-process the versions of each one, the tokenized versions of each one, and the tokenizers, the corresponding tokenizers. And we also actually want to call our pad function on each one of them. So we tokenize, we pad, and we are going to return those. But before we return the pre-process Y for so Keras sparse categorical cross entropy function requires labels to be in 3 dimensions. So we're simply here reshaping the pre-process Y here, the French, the labels, to make sure that it's the shape is compatible. And we just return those 4 objects. So we return the pre-processed features, the English text, the preprocessed labels, the preprocessed French, and then each one of those tokenizers that contains those mappings, those from words to IDs. And now here we have it. So we just create 4 variables and we assign it to this function, to this preprocess, passing in our English sentences and French sentences that we created before. And actually, let's go ahead. We're going to use this later. So let's grab the max English sequence length and the max French sequence length here. So we're just going to grab here these 2 variables that we just created, grab the shape and just grab the index 1. So there's 0, 1, 2. So let's grab the index 1, which gives us the length of the padded sequence here. So that would be the maximum sequence length for each one of those languages, and we're going to store it in these variables that we're going to use later. And we have the English vocabulary size and the French vocabulary size. We also want those. So we're going to grab our tokenizer objects that we just created and grab the word index member. So again, it's the mapping from words to indices, and grab the length of it. So because that contains the unique members, the unique words in the data, just the length of it will just give you what is the size of the vocabulary. That's the total number of unique words in each one of those data sets, English and French. And we're going to use that later. And here we just print it so we see what we have. So for English, it happens to be 15 for this data set. For French, the maximum sequence length is 21, and the paddings will correspond to this. Like English sentences will all be padded to 15, French sentences will be padded to 21, and then these are the vocabulary sizes. So there's a lot more unique words in French than in English for this particular data set. Okay, now that we have pre-processed, the next step is actually to go into our model. So we want to create a neural network architecture that is able to make this conversion, this machine translation from English to French. And we want to use multiple techniques and layers and so on that we'll see in a moment. And we can experiment with that as well. So a lot of hyperparameters that we can tune and so on. So before we get started, let's actually create a function here that we call logits to text, which is basically going to be a conversion from the output of our model, which is a probability distribution of class scores for what the model thinks is the translation for a given input for a given English word. And we want to actually, so we have a word in our dictionary, as we saw before here, word index. So we want an index word dictionary. We want the opposite dictionary. So what we're going to do is we're going to grab, this function is going to take in the distribution, the output of our model, and then the tokenizer for the particular language. And here for the tokenizer, it's going to grab the word index and dot items. This is so you can actually loop in a for a dictionary. So for word ID, that's the key and the value, we're just going to grab the ID and word. So we're going to create a dictionary that is flipped, where the key is the integer IDs and the values are the actual unique words. And that's how we're going to convert from IDs into words. So our model is going to give us back the IDs, and then we're going to convert to words so we can actually print out the value to the user, for example, or to ourselves, so we can see what the output is. And we're going to go ahead and add also a pad here, key at 0. So key 0, and then the value is pad. That corresponds to those zeros to that padding. And here we just want to return that. So for the prediction in NumPy np.argmax. So from our probability distribution at dimension 1, we're going to grab the maximum value. So what the model thinks is the highest probability, the prediction. Grab that, and then use that in our newly created dictionary, index to words. So grab that value, whatever it thinks that the index for the maximum, for the most likely output is, and just get the word for that, and then just join all of those words. It's a list comprehension, so we're going to join all those words to create a sentence. So once the model makes a prediction and gives these mathematical values as an output, this is how we're going to go back to actual text and print it out. So here, there's multiple things that we can do here. The simplest recurrent neural network architecture is this: is simply a sequence of words comes in English. For example, here the Quake Brown, it's a sentence. So for a given word, goes into our network, and then the output is the French translation, what the model thinks is the French translation. And then we're going to calculate the loss, and then minimize that loss here with a backpropagation through time, because we're looking at multiple time steps, right? It's a recurrent neural network. So this is the simplest case. And here for this particular example here, feel free to check out the link to GitHub in the description to look at this yourself if you want to see what these simple architectures, their performance, and how they behave. But we're going to look at the more complex architecture where we implement everything that we know. So here, the simple layer, and again, feel free to just look at this at your own pace. That's the simplest case. And then we have a second case where we use actually an embedding layer. So instead of just going directly into a network and outputting, we're actually going to put an embedding layer in between. And this embeddings layer is called word embeddings, and it's really a vector representation of the word that is close to similar words. So when you add a word embeddings here for a recurrent neural network, the model internally creates an n-dimensional space of vectors that represent words, each one of those words. And words that are similar in meaning to each other are actually closer together in this n-dimensional vector space. And words that are not that similar are actually farther apart. So it encapsulates more information about the essence of words by adding this word embeddings. Now, of course, it also adds more learnable parameters to your network. It's going to take longer to train. They may be overfitting issues. I mean, you have to take all of that into account, but general best practice is to actually add these word embeddings, because we'll just get a more rich information from our data set, and our model will learn more those fine-grained and specific relationships in the data. So word embedding. So convert our words into a vector representation, or we can just call it a tensor, right? Tensor is the general way of referring to a vector or matrix. Just say tensor. So tensor, and then now goes into our model, into a recurrent neural network. So that's a second way. Now another way, or something else that you can do, is to actually have a bidirectional recurrent neural network. So yes, you can add embeddings, but also what you can do is, without a recurrent neural network by itself only looks at past inputs of the sequence, so what came before for that particular time step. Now, what if you could look forward also into the future? So inputs or outputs that are yet to come. So with a bidirectional recurrent neural network, the model is able to learn not only from past inputs, but also from future inputs. So it's looking both into the past and into the future to learn relationships between the data. Now again, this also adds another layer of complexity, adds a lot more learnable parameters, but usually, again, this is also best practice to capture even more information in your data. And now another thing, this is more towards state of the art, is to use actually an encoder and a decoder type of architecture. So you can think of it as two separate neural networks. I mean, we're actually going to do it in just one, but you can think of it as two. And one's job is to encapsulate the mathematical information and relationships in your data. The encoder encodes the information from the input, and the decoder decodes that output. So usually the encoder looks at the input sequence and generates a context tensor, or a context vector that is usually referred to. And the decoder decodes that vector, that tensor. So again, it just adds some more complexity, so the encoder creates a matrix representation of that sentence, and then the decoder takes this tensor as input and predicts a translation as an output. And this in practice works very, very well. Now what we want to do is we want to incorporate all of these aspects into one custom model, and our hope and our goal really is to have the most accurate and the best predicting model. So again, we're using TensorFlow and Keras. So here we're going to create a function, a model underscore final, and it's going to take in 4 parameters. So first the input shape to our model, and then the output sequence length, and then the English vocabulary size and the French vocabulary size. And we're going to set a learning rate of 10 to the minus 3, and that's a hyperparameter that you can and should tune. But here for the simple example, we're just going to use that as the learning rate. So we're going to create a model variable and assign it to a sequential model from Keras. And we're going to go ahead and stack up our layers. So for our first layer, as we said before, is an embedding layer. So word embeddings here. So the input length here is the input shape here. At index 1, that would be the input to our word embeddings. That's really the length of our padded sequence or padded sentence sequence of words. And then here, these 128, these are just the number of units or neurons there, and that's a hyperparameter that again you can tune. And then the English vocabulary size. This is just the embedding layer. This is how it's going to convert. It's going to grab the vocabulary size in English, and it's going to create these internal vector representations for the input. And then the output for the embeddings layer is going to go into a GRU, gated recurrent unit, wrapped in a bidirectional layer. So the bidirectional layer, as we said, is just a wrapper that gives the model the ability to look forward and backwards in time to look at the relationships between data. And here, why GRU? Why not LSTM? You can use LSTM as well, but because our data doesn't have that many long-range dependencies, they're relatively short sequences of data, we don't need to look very, very far back where LSTMs might be a better fit. So GRUs in this case are faster and more efficient, so why not? So we use a GRU, which we imported earlier from Keras layers, and that was going to contain 128 neurons. So again, it's a hyperparameter. And for return sequences, we're going to say false, because here we don't want to return the sequences. We actually want to, because this is the encoder part of our networks. It's going to encode the input that's coming in, and we're not going to return the sequences yet until we're ready to decode it. So we set return sequences false, and there's a lot more parameters here for GRUs that you can set. Feel free to look at the TF Keras documentation for that. Now, the next, so the output of our GRU wrapped in a bidirectional layer is going to be the input for our repeat vector layer here. And really, this repeat vector, what it's doing is at each time step from the previous layer, it will get all of those inputs. It will repeat the inputs, but it will grab the different hidden states. So this is basically, with this repeat vector, we're able to grab information from previous multiple time steps and just put them all into one. And as you can see, we can look actually at the output here. So we have our embeddings layer, the output shape here, and then our bidirectional layer. And then for our repeat vector here, we're basically stacking up the outputs from our bidirectional layer. So we have all of those words. So 21 corresponds to the maximum sequence in French. So we're just stacking up the outputs here of our bidirectional layer. And we want the output sequence length, which is the French, and the max French sequence length, because the output of our model will be a padded sequence with maximum length equal to the French length, because we're outputting French translations. And now we have another, and then after we have that, then that is going to go into our decoder. So again, so this repeat vector here is representing, this is our encoded representation, our encoded tensor that represents the input, all of those relationships and between the data and the input. And then we have another GRU wrapped in a bidirectional layer, but now we're going to set return sequences to true. So here we do want to return the sequences because we're decoding that, and we're going to output a sequence or sequences. And then the output of that is going to go into a time distributed layer that contains a dense layer. So time distributed layer, what it does is assigns its input parameter, here in this case a dense layer, at each time step in our recurrent neural network. So at each time step we're going to assign a dense layer, and this is going to actually do our softmax classification. So we want our French vocabulary size, because the size of and this dense layer, so The size of our French vocabulary, as we saw earlier, was over 400 words or over 300 words, and that is actually the shape of our dense layer. And we're going to get a softmax classification on that on those outputs, a probability distribution for what the model thinks it is. So it's going to give a probability for each one of those. But most of them, ideally, once the model is trained, will be close to zero, and it will be the distribution will be pretty spiked, so to speak, at the actual word that corresponds to the correct translation. So that's what we have, and we wanted time distributed this dense because we want this classification to be happening for every time step. And here every time step means for every word, as every word is processed in the input English sequence. And here we're just going to display the summary of our model.summary, and you can see the embeddings layer, bidirectional, wrap, GRUs, and so on, and you can see the number of learnable parameters in each one of those layers and the total number of parameters in the network, and the output shapes as well. So very nice from TF Keras. And now we're going to compile our model, set the configuration for our model. So for our loss, we're going to assign a sparse categorical cross entropy. Why? Because this is a classification problem. We're classifying input elements of a sequence, English words, classifying them with a French translation at each time step. So that's why we have this particular loss function. Then for the optimizer, we're going to use Atom, adaptive learning rate. Very nice. So we just pass our learning rate here. And our metrics, we only care about the accuracy at this point. So for metrics, we just pick the accuracy and return our model. So that's our model function, our model final, that creates our complex model that is going to perform machine translation from English to French for us. So now let's actually go ahead and create our model here. So we create the function. So now let's call the function here, model final. Let's pass in the shape that is needed, so the input shape. So first we actually need to grab our pre-processed English sentences, and then we want to actually pad it with the max French sequence length. Why? So we already padded the English sentences with the max English sentence length. So why are we padding it again? Because our output now is going to be a French sentence, a sequence of French words. So we want to actually pad it further, extend it to what it, in our case, happens to be 21 for French. So we're able to capture the whole the maximum length sequence for the output, which is in the French language in this case. So we're padding our English with the French sequence length here, so adding a few more, adding a little bit more padding, so we can actually express the output properly. So that's it. So that's our input tensor here, TMP_x, and we're going to pass in to our model final the input shape, so the shape of that. And then for the output sequence length, we're going to say it's our max French sequence length. Again, that's what we want for our output. And then just the English vocab size and French vocabulary size, same thing here. And now we're going to train. So we have our custom model that we created object here when we call the fit method on it, the fit function on it, and we just pass in our tensor. So our features, which are our English pre-processed, fully pre-processed sentences. And now, so that's X, and then Y, the label. So the pre-processed French sentences, those are the labels. And those are already padded, obviously, because it's French already, and they've already been padded before. And then we also specify here, in this case, a batch size, epochs, and then a validation split. Here we're not really doing a validation split, but it's a parameter that you can pick as well if you split your data into training and validation sets. In this case, we're just keeping it simple. We're just really doing training just to show you how this works. But you can do that. And now we actually want to print a prediction. So once the model is trained, and as you can see how the training happens. So we start first epoch, second epoch, and here the model, the loss and the accuracy are getting updated. So we grab our custom model here once it's trained and call the predict method on it, predict function on it, and then we pass in. We're just going to grab one sentence here. So we're going to grab our pre-processed input, and we just grab the first element in that sequence. So the first sentence here. And we're going to pass for its second parameter the French tokenizer. So let's see what that actually turns out to be. That's going to actually convert our output. And we just go ahead and print that. Remember, we created the logItStext function before that is able to do this. So we get these integer IDs, or these as a result from our model, these predictions, these softmax classifications, these IDs, and then we're going to call this logItStext function that we created before to convert to actual strings based on our French tokenizer, which contains our vocabulary and our mapping. And that's what we have. It's very nice, very well trained model. It's able to, so we can here look. So is that the correct answer? It looks like it is. Even if it's not, it would be pretty close. But as you can see here, if you actually look at the code yourself, you'll see that for other architectures that are not this complex or don't take, for example, word embeddings into account or bidirectional wrappers into account, the accuracy is not as good. But here we're able to capture a lot of information, and it just works beautifully. So that's what we have. And now here you can also, as a standalone on its own, make final predictions. Here we just define a function. Feel free to look at it on your own. But our model is also able to again make predictions. Once it's trained, it's able to make predictions here. And this is just a regular sentence that we create here, and we're just doing so, and we're just letting the model predict on that. As you can see, it actually does pretty well. And that's the second sample that we saw before as well. And again, feel free to just look at this on your own and explore this code and these beautiful recurrent neural networks on your own to perform machine translation. So thank you for watching. If you have any questions, thoughts, comment below, and I will see you next time.